Thank you. So my name's Hendrik, and I'm from the founder of Systematico Data Engineering Consultancy. I'm really enjoying the time here in Amsterdam, by the way. I think Databricks is putting on a great summit. Coincidentally, I'm also reading a book right now that plays partially here in Amsterdam. It's by Harry Mulisch, a very famous Dutch author, The Discovery of Heaven. So yeah, it's a particular pleasure to sort of cycle around the city of Amsterdam and cycle along the canals. And I came into the conference today with a fiets, like a traditional Dutch bike. So yeah, it's great to be here. So graph-based entity resolution. Now, I admit, during my career, I came across lots of problems that I didn't even know they were graph problems. And once I discovered it, it greatly simplified the way I could solve the problem. And entity resolution, I would argue, is definitely one of those problems. But let's sort of go in from the big picture. I love this analogy. I'm sure you've come across it as well. It reminds us that the same way you can get your hands pretty dirty on oil, you can also get your hands pretty dirty on data. And really, it keeps on giving, because the analogies that come from the oil and gas industry, or generally industry, data extraction, data refining, data warehousing, really what we're after is building pipelines that are clear, well-documented, tested, and monitored, and that deliver data in the right format at the right time when it needs to deliver insight. And so how do we, as data engineers, go about that? Let's have a look at a high-level data pipeline. So all the way on the left, we've got data sources. They can be very disparate and many in number. And it's the task of data engineers to extract the data from these sources and move them, transform the data, often clean it and wrangle with it, move it into a data warehouse where then there's a lot more structure in your data. There's hopefully a common schema for the data that lands there. And this is then when the data can be picked up by data scientists. It can be used to train machine learning models. It can be used to derive statistical insight. It can be visualized in a dashboard or presented in a regular report. And so what we're focusing on is that upstream bit between data sources and integrating those data sources such that they can land in a clean way in your data warehouse. So from my perspective, there are three types of transformations that we'd be doing there, three ways to interact with these data sources. There's a sort of a first-order transformation where we've got a single data frame as an input and a single data frame as an output. And these could be things like deduplication, sort of like a distinct on that data frame. You might be adding columns. You might be mapping specific data into a schema. Second-order transformations. These are transformations where you have two data frames going into the operation and a single data frame coming out. So denormalization, as an example. There could be a join between two tables, and you have a common join key. But what about nth-order transformations, where you have the challenge of integrating multiple data sources, and that number n could be growing quite large? That's where entity resolution comes in. So hopefully that was enough motivation. We'll also next run through a very practical example on entity resolution, and that will give additional motivation. And then I'll walk you through that graph-based entity resolution algorithm to tackle the challenge that we're facing. I'll present to you a high-level data pipeline architecture for this specific entity resolution algorithm, and then we'll walk through the implementation in both GraphX and GraphFrames. And in the end, we'll have a discussion about where machine learning can play a role in entity resolution and where it could help. Right. So let's look at an example. So the example here is, what if you have an address book that has multiple records on a single person? So you can see here these 4 different records on our friend Harry. And the entity we're trying to resolve is that single person. So what we're looking for is a merge of all these records and collect the information on that one entity. In practice, those of you that have a Gmail account and you go to Google Contacts, A very simple example there is if you click on the duplicates tab, you might be presented with duplicates that Google found for you, and you're prompted to merge that yourself. So it's actually automatically detected, but it is up to you to decide whether these are actually duplicates and ought to be merged. So let's get back to work on resolving our records. Now, here is sort of a more complete data set. All our records from different sources. As you can see, I've listed here the sources on the right-hand side. So these records could come directly from your phone, for example. They could be in your Gmail. They could be in Outlook, from different sources. And you combine them all in a single data frame, in essence. Now, the challenge here is you don't have a single join key that allows you to just put these together in one step. So that's why we're pumping them into a single data frame or a single table. And then when we look at how these are connected, and you can already see the graph problem coming in here, we've got situations where maybe we've got a connection between record 1 and record 3, for example, where they have the same name, and in this case, they have the same name. Now, record 3 and 7, on the other hand, has a common phone number. Record 1 and 7 are only connected via record 3, however. And that's where you instantly see that this is a graph problem. So let's walk through the algorithm itself. I've now taken that data frame and sort of distributed it and basically visualized it here as a graph. We've got the same 7 records, the 3 from my phone, and yeah, I've highlighted them with these big blobs, 2 from Gmail, 2 from Outlook. We now take each record as a single node. In the second step, we create edges between those nodes based on similarities between the nodes. And as a simple rule, we'll just use a match, an exact equality, across any of the attributes. So let's draw these edges. Now you can see 1 and 7 are connected only via 3. We then want to connect these, sort of draw and collect all the nodes that belong together and merge the information consolidated into 3 entities that remain. And those are the 3 people that we, in the end, have in our consolidated phone book. Okay. So let's get back to the architecture. Now, I mentioned that you put all your records from different sources into a single table or data frame. Now, how do they get there? So when we integrate multiple sources, usually what would happen is we'll take a straight copy, sort of a raw copy of our data sources and warehouse that. And now you might remember that as this bronze source that was talked about yesterday by Michael in the keynote. Once we have a snapshot of that, we would then perform mapping and cleaning operations such that we get a clean version of these individual source records. And that's the second step. And then we append them all. As they're clean, they already are in a common schema, so we can append them straight into a single table, from which then the resolve operation, which we'll go through right next in the next step, would run off that appended records table, which yields a resolved records table. And in a subsequent step, these resolved records then get merged into entities. These form your consolidated nodes. So that will be, in essence, your silver source that is mapped and cleaned, and your golden source, in a way, once it's merged. So technical implementation. Apache Spark comes with a neat, quite powerful amount of graph analytics, and that is packaged with the normal distribution in GraphX, which has a Scala API. And on the more experimental side, we've got GraphFrames that has both a Python API and a Scala API. So we'll have a look at how to implement this with GraphFrames in Python, using the Python API, and then we'll run through the same thing in GraphX using the Scala API. So let's get started in GraphFrames. So imagine at the bottom, just as an example, we've got this data frame. So we've got information on people, similarly to a phone book. Now we've got a few columns here, and we'll use a subset of these, which I call the identifiers, to build, that we use as rules, that we look for matches across them. So we've got, for example, social security number and our email, and the other columns, those will be attributes, sort of labels and information on the property graph, but that we don't use to match any of the nodes together. Now, as a first step, the very important thing is we'll give those records an ID. So that is then the ID, the record ID, which is also the ID of our nodes. The next step is edge creation. So we define which columns in our data frame we want to find matches within. Now, as we need to compare each record to each other record, we'll basically perform a self-join on our record data frame. And in order to do that, we'll just create a mirror. And we'll underscore each column. We'll append each column with an underscore to allow us to reference them individually. And that's what's happening here. We then define the conditions on which we join. And so here we say, for all our match columns, we want them to be equal, except for the ID column, because we don't want any record to be compared to itself, or at least not an edge created between that record, because the information within that record is obviously, there's always obviously a match. So it's kind of taking out the diagonal from that self-join. Now we reduce, so we exclude the record from itself, and then for all the other records, we look for any matches. That's why there's the OR condition here, as you see in the lambda function. So wherever you find a match, an edge will be created. So that then gives us our self-join. We'll join the records on its mirror given those conditions. Now to make that a little bit clear, here is that condition, those conditions, what they look like. So we don't want record ID to be the same, and we want either a match across social security number or a match across email. So that gives us our edge list. Now we've got our nodes, which are our records, and our edge list, which records need to be connected. And from that information, we create a graph. We set a checkpoint directory, which truncates our query plan, and then we can run connected components algorithm. So this is a functionality that comes packaged with Spark in both GraphFrames and GraphX, and it basically kicks off a depth-first search and looks for whichever records are connected in the same component. Once that's done, we can move on to the merge step, where we take the connected component graph and we group by the components. And when we group by those components, we can use aggregation functions such as collect set or collect list to collect all the information that you have across. So these would go into your attributes, and all attributes, let's say phone numbers, that you find across those records that are connected, it would collect a set from it. Okay, so moving on to GraphX, we'll implement that using the Scala API. And Scala being a strongly typed language, we have to first define the schema of our data frame. So you can either assign an identity column to your record in the run, or you might just save the record ID directly with your data frame. But it's very important that it is there, that each record has its own unique ID. And then you've got your identifier columns, such as a social security number and email in this example, and then any attributes. So I've sort of abstracted all the other attributes here in the attribute field. So let's make sure there's an ID column on that data frame. Now in GraphX, we need to turn our data frame into an RDD actually. So we're doing that here. We're creating a nodes RDD, which is basically just an RDD of vertices. So each row is turned into a vertex, which doesn't have any properties. That's why we'll just give it here a 1 because we're kind of interested in the structure rather than any properties on it. OK, edge creation, very similar to what we did in Python. We'll create a mirror of that record data frame. So here, we're just appending an underscore in front of our column names so that we can reference them. And then we create those conditions. So these are the same conditions, avoiding the diagonal, not joining on the identity column, the record identity, but any other matches across our identifier columns. We'll join as a data frame. This is the self-join. And then we create an edge RDD using the both ID. So this is the source and the destination of our edge, basically. We get that as an edge for both records. And again, you can see here there are no properties attached to these edges. It's a very thin graph structure in a way. So once we have those two RDDs, the nodes RDD and the edges RDD, we run our connected components algorithm. And once we've run that connected components algorithm, we need to turn our resolved entities back into a data frame, which we'll do here. Now, you can see that the entities data frame here has a column that is inconveniently named _1. That is your record ID. And you join your record ID back onto your original record data frame. So that gives it the second column in your, just down below here, is your entity ID column. So these are the connected components. And we group by that to collect all the information that we need, such as name, phone number, any of the attributes that we want to collect. Right. So in a way, we could see this resolve operation abstracted as a first-order transformation where we have an input data frame, which is essentially your appended list of records. We've got an output data frame, which is the resolved records that can then be merged, and the extra configuration that goes in this case, will be just the column, the identifier columns that we match across. So in terms of evaluation, now evaluation is challenging, actually, because it really depends on what kind of data you're dealing with. The first thing you do is look at how your records are distributed across the sources. So do you expect an equal distribution? So as you can see here, sort of like a high overlap between sources. And these could be many sources, not just two, as is highlighted here by the Venn diagrams. Or is there little overlap? And this is what you would want to find out, whether that matches what you expect or whether that matches what you're looking for. In some cases, you're trying to actually find a perfect match between them and unsurface any data or at least flag up if there seems to be data missing. So in certain use cases, you might want to try to add data sources to complete the picture. Now, very important are also sort of conflicts in the business logic. So if you imagine social security number is a unique identifier for a person, or at least it should be. So as you run through your connected components, if there are any connected components that have two social security numbers, that seems to be a clash in your business logic. And that's one thing to investigate. Why is there a connection made between entities that sort of things that could be two people, and investigate that. It could be a data quality issue, but it could also be, in fraud cases, it could actually be something that you want to surface and to take action on, maybe blacklist a transaction or something. Okay, so shifting gears a bit. Now, evolving entity resolution, this is the discussion about how we can use machine learning to evolve our entity resolution algorithm. And really at that point, it plays an ancillary role in my opinion. But let's have a think about it. So one thing to remember is that what we're doing here is pairwise comparison between those records. And so instead of using a simple matching approach and just finding equalities between records, we can move to, well, let's call it a more nuanced way of creating a match between records. And that is by, rather than just saying, yes, it is a match, or no, 1 and 0, we can say there's a probability that these match. And that probability could be based on distance measures between any of your identifiers, or it could be based on a model that has been learned on a corpus of string comparisons. And there's some in the literature that might be useful there. It could also, that probability of whether there is a match or not could also depend on temporal data. So basically how old your records are. And you might put a threshold on how much time you want records to be apart. Especially when, as data changes, that might be pretty important to not match old data to new data because things might have gotten out of date. But the issue here is that the edge creation is the very computationally heavy step because we're doing pairwise comparisons. And we can, if we have a large data set, doing pairwise comparisons can become very expensive and can be an n-square problem. So how do we reduce the amount of computational load there? So one approach would be to apply clustering or location-sensitive hashing to our data set and find suitable partitions across our records such that we can minimize the amount of comparisons that we do. Now, really, once you get, my suggestion would be to start simple and to start with simple heuristics and then gradually, as you explore your data, to move up the complexity gradually. And one thing that could be quite challenging but also quite rewarding is if you have the possibility of, well, if you accept false positives or false negatives. If you have that luxury, you could use the weighing of your edges or the probability whether there is an edge or not. You can use basically a smart filter, and depending on how much false positives or false negatives you are willing to accept, you can train a classifier to qualify edges or not. Basically, depending on your use case, remove edges if they become too weak, if there's not enough similarity between records, in essence. What you would be going for, really, is using machine learning upstream to increase the quality of your data, the quality of your connections between records, and connections between, well, to create your entities, to increase the contextual information, so the reach of how much information you can gather on individual entities. But it is very use case driven, whether you can really span your net very wide there. I think a careful approach is necessary because what you're after is providing a corpus of knowledge, so that golden source, the merged entities, they will be used for something. And more often than not, in this case, they will be used for human insight, actually. As you could see with the Google example, they leave it up to you to decide whether these matching records are actually the same person. So assisting, having entity resolution there assist sort of forensics and discovery for analysts is more crucial than sort of automating the human out of it. Now, I think a good way to try this out is just to give it a try. I've collected for you the information and the code examples here in a GitHub project, which you're welcome to have a look at. And also, the easiest way to get started is just using a simple Docker container. I've bundled GraphFrames here with PySpark because it doesn't come sort of out of the box. So if you're using that Docker container, you can just get started. And GraphX comes bundled anyway. So any container or any setup that has Apache Spark will come with GraphX and will be ready to go. So the main things for you that I want you to take away today is that in this setup, your sources, your records, all land in a single record table. That's sort of the coalescing point of our data pipeline. At the core of it is a connected components algorithm, very powerful algorithm that just comes free in Spark in essence. But the edge creation is the expensive operation, and any optimization and improvement, both in the way you structure your data, the way you partition it, is computational load saved. Obviously, Spark is pretty clever, but any way you can help it reduces how much money you spend on computation. And it is a batch operation because you're collecting a single corpus and then you run that as a batch. So that obviously has to fit into your architecture. Now, once that batch operation is done, it gives you a corpus of knowledge, as I would call it, something that you can then take and move into different data sources or different databases, whether that would be going to Elasticsearch or whichever way you want to serve it, whichever way you use it in production. It is something that should fuel, let's say you're looking for a fraud detection system. It needs to be accessible in a way. So you're producing a data set that will end up somewhere else. So that point, that's really it. Thank you very much for your attention. I'd be happy to take any questions.
Okay, we have time for a few questions. Please raise your hand and then I'll bring you the microphone.
Thank you for the presentation. As far as I know, entity resolution is, let's say, well-studied field, studied in decades. My question is, if you compared your algorithm with the state-of-the-art algorithms in the field, and the second question is whether you evaluated precision recall accuracy of your algorithm on different data sets, just to give an idea, you're 80% accurate or 60%. Thank you.
Yeah, I think that's a good point. So it's been around for a long time, and I think a lot of the research that's gone into the field is trying to make the pairwise comparison easier, or make the pairwise comparison more intuitive. Now, in this case, the resolution is, it really depends on, in essence, on your data set. It's sort of an algorithm to have a go at. I've had sort of a corpus internally, and there, in the GitHub project, there's some dummy data. But I think there's an issue with sort of data being available for entity resolution. There's some entity resolution on sort of multiple entities, such as authors and institutions and papers. So it actually stretches multiple entities. Now, in this case, the example is on how to resolve entities for single entity. And I think that's one of the things where I would be very delighted actually to kind of find a robust corpus to test against, but not one that kind of has sort of that multi-entity architecture, but rather a single entity that you're trying to resolve, like a standard data set. I think that's something, yeah, to work towards. That'd be nice to have like a standard reference set for the future.
So you don't have like accuracy. So you don't have like precision recall figures for your algorithm.
No, because it basically depends on the rules. Like the rules here, they're very simple, right? It's just sort of like straight matches. So depending on what data set you have and how many matches you find in there.
Hi, thanks for your talk. I was a bit surprised by the last key takeaway that you mentioned. Why do you say that it has to be a batch operation? Well, I'm confronted to these kind of problems, but in almost stream, like, well, it's batches, but which comes every 1 minute or so.
Yeah, yeah. So
where I have to decide, I have a new input, and I have to decide if it corresponds to one of the entities that I already manage, or if it's a new one.
Yeah, yeah. Yeah, I think if you think about it as a streaming problem, I think that would mean you would go about it completely differently, actually. Or it also depends. In this case, the assumption is that all data lands at the same time. And so if all the data is there at that point, then you perform the self-join, which is then that expensive batch operation. If you've got records coming in, so if you already have a corpus of knowledge, if you already have resolved entities and you're actually looking for a match across those, then I think, yeah, the architecture would look completely different. And I think also the problem would look very different. I think you would go to, it turns into a search problem, I guess, where you've got a record coming in and then you'd be searching across a corpus for any matches. But it's not really that you're sort of running an analysis on a whole collection of records. But I think it's once you want to get started one way. And that could be your way to get started, build up a corpus, build up intuition around the data set. I think it's the kind of operation that helps you find structure in data, especially when it comes from multiple sources. And then, so often you can sort of like get a feeling for them individually. You can gather statistics on sources individually, but once you've got them in this format, you append them to the same table, you then resolve and you merge. That gives you a good understanding, and with that sound understanding, you can then implement sort of evolve in another way. For example, a streaming pipeline that individually checks for any clashes. I think in the case of fraud detection, I would say one of the major applications for integer resolution is fraud detection. That will be your natural path.
Okay, thank you.
Thank you.
Other questions?
Hi, thank you for your talk first. I've got one question regarding your possible extension where you have a probability score on the edge. How would you deal with that when you apply the connected component algorithm? Would you take the probability into account? Would you apply a cutoff and ignore low probabilities?
Yeah, that's a really good question. So I think you want to run essentially a filter, essentially you want to qualify at which point you believe an edge to be resilient, to be sort of robust. Yeah, basically turn that probability once you have an established measure. Maybe at 80%, you'd be confident enough for there to be enough similarity for that to constitute an edge. So it'd be just a filter that you run on your edge list, and then run the connected component algorithm subsequently.
Hello, thank you for your talk. We are doing quite similar thing as you were doing, so it was really interesting for me. Yeah, first, I have just a quick tip for your code there, where you are doing this self-join and renaming all the columns. I'm using that. I'm aliasing the data frames so I can reference them, and it's a little bit easier in my point of view. But just a quick tip. And the second thing, yeah, there was the question about probabilities of these edges. And your solution was like to remove the edges at all, but maybe it would be nice to propagate the probability to the edges after the edge, if you understand me. So I don't know if it's not dealing with that in that way, because it's forget those edges at all. Do you have a solution like how to propagate the probability in the relationships after, in the whole graph, basically?
Yeah, I think that's a good point. To your first point about, it's very interesting to see how often that problem pops up. And I would say entity resolution, I think that it's kind of like that case where you've got a lot of examples around transformations, you've got a lot of examples around join and how to use them. I think entity resolution should be a common example for data engineers because it is such a common issue, and it's a great way to sort of integrate data sources. I think it props up plenty, and actually having a more widespread discussion on what are the best practices in Spark would be great. Yeah, regarding the probability, I think that's I'd have to think about that a little bit more, to be honest. I think it's a good point because it gives you extra information, so you would want to kind of capture that. There's definitely a point in not only saving the records. So in that data pipeline, you saw like specific stages, and I would recommend to persist actually more than, especially as you're developing it, as you're standing up the pipeline, persist more than you would normally, or that you would intuitively do. And in some cases, persisting the edges specifically can also be really impactful, especially as you're developing it, diving into it. In the end, we're much better at reasoning than computers still are. So having that available, maybe being able to visualize it, that could be really useful.
Okay, we're out of time. Don't forget to rate the session in the Spark Summit app. And please, let's thank our speaker again.
Thank you.